Good morning, my dear friends, present in the conference of ICDSMLA 2021, respected chairs of the technical session. I am here to present a paper titled An Anchor-Based Fuzzy Rough Feature Selection for Text Categorization. Myself is Ananya Gupta from the Department of Computer Science, Assam University, Silchar, India. The presentation outline is as follows. The section 1 is on introduction. Section 2 is the brief review of the concepts. Section 3 is the proposed anchor-based fuzzy rough feature selection. Section 4 is on the experimental results and Section 5 is on the conclusions. Big datasets are characterized by large dimensions consisting of hundreds and thousands of features with uncertainties and imprecision. Therefore, it becomes a challenging task to represent these datasets in memory-short environments. Feature selection, as we all know, enables dimensionality reduction of such datasets by finding subset of relevant features from the original feature space. To produce an optimal feature subset, an ideal feature selection technique should therefore be capable of handling interdependencies and uncertainties that are present in the features. In this paper, a new hybrid feature selection technique called anchor-based fuzzy rough feature selection has been proposed. It is based on the concepts of anchor graph and fuzzy rough feature selection and has been applied in the domain of text categorization. The proposed technique, ABFRES, is a hybrid of anchor graph and fuzzy rough feature selection. ABFRES is proposed with the intention to overcome the inherent problem of representing big datasets in memory-short environments. ABFRES addresses the uncertainty in features, retains the interdependency amongst the features while maintaining the predictive accuracy in memory-short environments. The predictive accuracy of this technique is evaluated in terms of the clustering accuracy. Coming to the section 2 of the presentation, which is on the brief review of concepts, let us first discuss the concept of anchor graph. The anchor graph is nothing but a graph-based learning technique which constructs graph with data points and anchors. Now, anchors are nothing but landmark points on the data sets that are selected on the basis of the cluster centers of the k-means algorithm. Smaller subset of features can be represented using anchor graph, wherein the landmark points can be linearly combined with the rest of the data points. Subsequently, an adjacent matrix is built that measures the weight between the anchor points and the m data points. This adjacency matrix is of much lower dimension than the original feature space and can be visualized in a d-dimensional space having dimension d cross m, d being the number of anchor points and m is the number of data points and d is much less than n. Anchor graph construction is also advantageous in the sense that it does not use the KNN strategy of graph construction, and secondly, the construction of inverse normalized Laplacian matrix is avoided. Both these KNN strategy of graph construction and inverse normalized Laplacian matrix are infeasible in case of large datasets. This slide is on the mathematical formulation of the anchor graph. As I've mentioned in the previous slide that anchor graph constructs an adjacency matrix which is scalable. So the basis of the scalable adjacency matrix construction is represented by the mathematical formulation on equation 2. This slide is on continuation with the mathematical formulation of the anchor graph. The W represents the adjacency matrix constructed in the anchor graph, and Wij is greater than 0 when there is a correlation between the anchor points and the data points, and it is equal to 0 when there is no correlation between the data points and the. Continuing with a brief review of concepts, let us focus on the fuzzy rough set theory for feature selection. Fuzzy rough set feature selection reveals the data interdependencies. It reduces the dimensionality of the data immensely, and it can be used for feature selection wherein degrees of membership are used, and it minimizes the loss of information during the process of feature selection. Fuzzy rough set feature selection can successfully handle data dependencies and reduce the dimensionality of the feature set without compromising the performance of classification and clustering. It retains the most discriminative features, while the redundant and irrelevant features are removed without information loss. This slide is on the mathematical formulation that has been used for fuzzy rough set feature selection. The fuzzy rough set feature selection uses the dependency measure between attributes P and Q given by the formulation in equation 7. Coming to the section 3 of the presentation, which is the proposed anchor-based fuzzy rough feature selection. The proposed technique works on the hybrid concepts of anchor graph and fuzzy rough feature selection. The algorithm begins with m data points with n variables, that is the n number of features, u the number of anchor points, and s is the number of nearest neighbors. So in the first step, the anchor points need to be selected using k-means algorithm. Second step, adjacency matrix is constructed between the anchor points and the data points given by the formulation as shown in the mathematical formulation. In step 3, the smoothness parameter is estimated as in the mathematical formulation given in the step 3. In the step 4, the adjacency matrix produced in the anchor graph construction is assigned to the reduct R. In the step 5, for each data points belonging to the reduct, we remove the data point under consideration from the reduct. In step 7, we calculate the fuzzy rough dependency measure as per the equation 7. And if we find that the fuzzy rough dependency measure is less than 1, on consideration that the data point under consideration has been removed from the reduct, then we retain that particular data point in R, else we remove it, and finally we return the reduct R. The output of the algorithm is the optimal reduct R. Coming to the section 4 of the presentation, which is on the experimental results, the datasets that have been used for the experimental are TD-T2, the Reuters 21578 and 20 NG dataset. The TD-T2 has 9394 instances with 36,771 attributes in 30 classes. Reuters datasets has 8293 instances and 18,933 attributes in 30 classes, and the 20 NG dataset has 18,846 instances and 26,214 attributes in 20 classes. The evaluation metric has been used are accuracy, and another evaluation metric that has been used in this case is the normalized mutual information. So both these metric, that is the accuracy and the normalized metric mutual information, has been used for the purpose of experimental analysis and results. The results that are obtained with the proposed technique, that is ABFRES, is compared with the unsupervised and supervised fuzzy rough feature selection technique. The techniques that have been compared with our proposed technique is the unsupervised fuzzy rough lower approximation based feature selection, denoted by UFRFS, unsupervised fuzzy rough boundary based feature selection, denoted by BUFRFS, unsupervised fuzzy discernibility based feature selection, DUFRFS, supervised fuzzy rough lower approximation based feature selection, FRFS, supervised fuzzy boundary region based feature selection, BFRFS, supervised fuzzy discernibility based feature selection, DFRFS. The datasets which we have considered in the experiments are labeled. However, before using the UFRFS, BUFRFS, and DUFRFS, the decision variables are removed from the dataset as they are unsupervised approaches and they had to be applied on unlabeled data. Moreover, our proposed technique ABFRFS is also unsupervised, and so before using it on the dataset, the labels have been removed. The quality of feature subset produced by the techniques ABFRES, UFRES, BUFRES, DUFRES, FRES, BFRES, and DFRES are evaluated using the k-means clustering. Two separate approaches are adopted when generating the reduct for the considered datasets. First, a near-optimal reduct is selected from the dataset, and secondly, a reduct is selected for each of the tenfold cross-validation, and the average for each fold is obtained. The reduct size produced by the considered feature selection technique over benchmark datasets are reported in Table 1, and Table 2 reports the result of average reduct size produced by the above-mentioned techniques using tenfold cross-validation. From Table 1 and 2, we can conclude that ABFRES produces a dimensionality reduction of 98% on TDT2, 98% on Reuters, and 99% on 20ng dataset. ABFRES compared to the supervised approaches underperforms in terms of the reduct size. ABFRES produces the smallest reduct with Reuters dataset amongst the three considered datasets, and in remaining two cases, the reduct produced by ABFRES has a near comparable performance with the other unsupervised approaches. The execution time of ABFRES is compared with the other considered techniques and reported in Table 3, and has been found that it has a greater runtime than the other considered unsupervised techniques, probably because of the extra cost incurred due to the construction. K-means clustering is performed to evaluate the quality of the reduct produced for a given cluster K. 30 tests are carried out randomly, and the average performance is recorded. The k-means is applied 20 times with random starting points, and the best results are recorded in terms of the objective function. And the clustering is done using reduct obtained by various techniques for k equal to 5, 10, 15, 20, and results are reported in the table. The clustering accuracy of ABFRES with the reduct show the best result for k equal to 5 for TDT2 and k equal to 15 for 20ng dataset, highlighted in green. And for the rest of the cases, ABFRES has close performance for different values of k. The NMI measure also shows that the ABFRES produce the best result with TDT2 for k equal to 10 and for k equal to 15 with the 20ng, and in the rest of the cases, it has close performance with other techniques. Coming to the conclusion, the paper proposes a new technique, ABFRES, based on anchor graph and fuzzy graph feature selection. The technique efficiently represents big data parsimoniously in memory short environment, and at the same time reduces the data dimensionality immensely while retaining the predictive accuracy. It selects the most discriminative features that preserve data dependency and tackle imprecision and uncertainty. Experimental results reveal ABFRES produce a dimensional reduction of 98% on an average on the datasets, and the quality of reduct produced by ABFRES evaluated in terms of the predictive accuracy of k-means clustering show close comparable performance with other considered fuzzy graph feature selection techniques. With this, we come to the end of the slide. Thank you all.